Welcome back to CF 712. In this session, I'm going to talk more about regular languages. Pumping lemma for regular languages is really a tool for helping us explore what languages are regular and which ones aren't. Let me just state it first. Let L be a regular language accepted by a DFA M with K states. Let Z be any string in L with the length of Z being greater than or equal to K. Then Z can be rewritten UVW with the length of UV being less than or equal to K, the length of V being greater than 0, and UV to the I, W, will be an element of L for all I greater than or equal to 0. The basic proof is dependent upon the fact that the DFAs are finite, so they have a fixed number of states. In this case, we're assuming the machine M has K states. But if you think about a string that's longer than K, then there's some state in M that's supposed to be visited more than once while accepting Z. Right? There's K states, but there's more than K symbols in the input. We've got to visit one of the states more than once. So there has to be a cycle, right? We have to come back to a state, and that pathway from the state back to itself defines a cycle in the states. And we could go around that cycle arbitrary number of times and then finish our trip to the final state. So the strings recognized by going around the cycle more than once, twice, 3, 4, 5, they all have to be in the same language accepted by the machine. So the diagram, you might think of it like this, where I've sort of deconstructed the finite state machine into just its critical parts here. Right, there's some pathway to get to the entry point for the cycle, and if we think of that deconstruction algorithm that generated a regular expression from a finite state machine, right, I could eliminate all the states in between the initial state and the beginning of the cycle, call that U, the regular expression matched by that U. Then I can do the same thing. I can eliminate all the states on the cycle, call what's matched by that V, and then from the end of the cycle to the final state, deconstruct again and get another regular expression W. So it just makes it obvious that U, V to the star, W are all accepted by the finite state machine. Okay. So again, just derived strictly from the fact that the finite state machines are finite. Well, how can we use this? Well, consider the language A to the N, B to the N. The question is that regular? Can a finite state machine match those languages which start with a sequence of A's, and then where every string in the language starts with a sequence of A's and then a matching sequence of B's? In other words, a string of A's and a string of B's are the same length. Is that regular? The proof is by contradiction here. Assume it is. It's recognized by a DFA with K states. So if it's regular, it's going to have a DFA. DFA is finite, so there's a K. There's a number of states. Let's call it K. And then consider the string now, S, which is K A's followed by K B's. Clearly that's in the language L. Okay, same number of A's followed by same number of B's. It's just that it's a particular number of A's now. It's a large number of A's. It's the number of A's that correspond to the number of states in the DFA. Well, we can apply the pumping lemma now. So S is equal to A to the K, B to the K. So S, the length of S is greater than K. So that means we have to be able to decompose it into UVW, where the length of UV is less than or equal to K. The length of V is greater than 0. But we've chosen this particular string, right? So the length of UV has to be less than or equal to K, that means U and V has to be made up of only A's. Therefore, in particular, the V portion of UV, the V portion must consist of only A's. Let's call the length of V to be N. And we can pump once to produce the string S prime, which is K, A to the K plus N, right? We've added N A's by pumping once, and we still got K B's. And that's supposed to be in the language, but clearly it's not, right? It doesn't start with an equal number of K's followed by, equal number of A's followed by an equal number of K's. The pumping adds A's but doesn't add any B's, so it's out of balance. So it's a contradiction. It can't happen, so L must not be regular. Now the key thing is when you're using a pumping lemma is you don't get to choose the U, V, and W. You have to choose a string that will force U, V, and W to be what you want. So in this case I chose this big string, A to the K, B to the K. The fact that A to the K and the pumping limit tells us UV is less than or equal to K tells me that V has to be A's. And I don't know where the U boundary and the V boundary is, but V must consist of only A's. Again, I don't get to choose the boundaries between U, V, and W. Your proof must work for all possible U, V's, and W's. Okay, so keep that in mind. That's the key point. All right, but again, this is the prototypical string that's not recognized by a DFA. And just intuitively, just think about it. I mean, I can't remember, right? I can't remember these infinite, potentially large, growing to infinity number of A's, right? If I only got K states, I can't remember how many A's there are beyond K. I mean, that's basically the intuition of the pumping limit. The use of the pumping limit just makes that clear. Okay, so this is the prototypical thing. If you think about this, this is like the matching parentheses problem, right? Regular languages can't match up parentheses. All right, what other properties of regular languages can we deduce? Well, we start with the first three that were just a result of the definition, right? Regular languages are closed under union. So if L1 and L2 are regular languages, then the union of L1 and L2 is regular. Again, that's just by the definition of regular languages. Similarly, the product of two languages, if they're both regular, it's going to be regular. And the closure of this language, if L1 is regular, is also going to be regular, just by the definition of regular languages. So we knew that coming in. But look at this. Is the complement of a regular language regular? Well, the answer is yes. And the argument is take the DFA that recognizes L1 and construct a new DFA from it by making all its final states to be non-final and all its non-final states to be final. So any string that was accepted before is not accepted now. Any string that was not accepted before is accepted now. Okay, and that's, of course, that's the complement. So again, a construction proof. You give me the DFA, I'll give you the DFA for that recognizes the complement. All right. Finally, regular languages are closed under intersection. And we can show this by DeMorgans Law. Right? DeMorgans Law says intersection of two sets is the union of the complement of the sets and then complement that. And we just showed, we know it's closed under union. We've showed it's closed under, regular sets are closed under complement. So therefore this whole thing is a regular set. Okay. DeMorgans Law. I mean, I always have to stare at this diagram to remember why it works. Okay. All right, well, we can use intersection. If we know it's closed under intersection, we can use that to argue about whether certain languages are regular or not. So consider L to be the language over AB consisting of all strings with an equal number of A's and B's. Is L regular? So the A's and B's can be scattered anywhere, but the only strings that are in the language as if there's an equal number of A's and an equal number of B's. Okay. The question is L regular? Well, consider M, the language described by the regular expression A to the star, B to the star, right? That's a regular expression, so clearly that's regular. And now let's intersect A to the n, B to the n greater or equal to 0. Sorry, let's intersect L and M. L is, again, this language that has an equal number of A's and B's. M is this particular regular language defined by this. And if we think about that, the intersection of that is this set, A to the n, B to the n, right? Got an equal number of A's, and we intersect that with this A to the star, B to the star, which is regular. And it's going to be exactly that set, A to the n, B to the n. But we just showed that set is not regular by using the pumping lemma. Therefore, this set, L, can't be regular either. Okay? So that's an example of using intersection. So that's the pumping lemma, and then some properties of regular languages that follow from using the pumping lemma, and how to use those tools to consider whether a language might be regular or not. Okay, let's stop here.